So we're going to see, we're going to give a real workout to Bash Films because I will ask your forbearance in advance. I have a bit of a cough. And those of you that are watching this on video, if you see little skips, I think that's Bash Films doing their job. Those of you who are in the room, it's going to be a fun ride. So the premise of this talk is that you will be a better C++ programmer, a better user of the STL, if you understand where the STL is coming from. What are we trying to accomplish? Why is it designed the way that it is? I think often when we teach C++ programmers about the STL, we don't do enough of what the background, what we're trying to accomplish. Instead, we just jump right in and we start saying, these are how the containers work and this is what you do. And I think we miss the big picture that way. So what we're going to talk about today is Alexander Stepanov, the man who coined the term generic programming, who invented generic programming. He created the standard template library and he wrote elements of programming. And you're going to figure this out very quickly, but I'm going to come right out and say it. He's my idol. I have great respect for Alex. So I am going to say some critical things about some of his decisions, but it's with love. And most of the things that I will point out that are problems are things that Alex taught me and said, yeah, this was a mistake. We should have done it differently. But the thing that I admire most about Alex and what I think drove his career and drove the creation of the STL was a question he asked. And the question was, can we write algorithms generically, so we don't have to rewrite them every time we use them, without a loss of performance? This is what drove his career. This is what created the STL. And what I think is sad about this is that nobody else had asked this question yet, or at least nobody had tried to answer it. And this is amazing to me. And the thing that's sadder still is that the attempt to answer this has only been done now in 2 languages. And both languages had to be modified extensively in order to be able to answer that question. So we have literally thousands of programming languages out there, and they're not designed to answer this particular question. So I'm calling this the legend of Alex Stepanov because some of what I'm about to tell you was told to me. It's oral history, people who shared Alex stories with me, and I haven't necessarily been able to document everything. And so I'm not certain that was true, and I'm not certain that I remember it completely 100%, so I don't really want to be the source, the ultimate source on Alex. But I do know that he was born in Moscow in 1950, and this was the USSR during the Cold War. The USSR was very much about promoting anything that reflects well on our society. And so they were very much about athletes, chess masters, musicians, poets, and mathematicians. And so they had a program to identify math geniuses very early on. And so he was identified very early on as a math genius, and he was given, sent to Moscow State University, where he had, kind of the best of tutoring. He earned what we would consider the equivalent of a PhD very young. I don't know the name. Someone told me at what age. It was really young. It was surprisingly young, but I don't remember the exact name. But Alex always thought of himself as a mathematician. He would say, I'm not a programmer. Of course he was a programmer. He was a programmer. But he'd say, I'm not a programmer, I'm a mathematician. But his area of mathematics was information processing. So computing was what he studied, but he studied it from a mathematical point of view and considered himself a mathematician. And he referred to Hardy, who's a famous mathematician who actually formally apologized. He said, I hope nobody ever uses my mathematics in the real world, because he thought of mathematics as like art. You just do mathematics for the beauty of mathematics. That was not what Alex said. Alex said, Hardy's hope that his mathematics is never going to be applied is not for me. Alex wanted what he did to be used by real people in real situations. And that's an important point of view for what drove him. After he got out of college, he worked at a hydroelectric power station in Moscow. And he credits this with teaching him a lot of things about real-world programming, including things like real-time operating systems and very much about reliability of code. Because as he once said in an interview, it's very hard to reboot a hydroelectric power station. So Alex came to the US and started working at General Electric. Now, this is part of the stuff that I am not really able to document, but when he left the USSR, they stripped him of his degrees. And I think that was very much why, as we talk about him, you'll see that all of his work, with one exception, was in industry. He was doing research in industry, not in academia. When I talk to him, I'm going to have a lightning talk later tonight to talk about this, but when I talked to him about the academy and academia, he was very, very much about that. In fact, when I worked with him, I was running two conferences. I was running this conference and CPPCon, and I begged him to come and speak at either of the conferences or both of the conferences. He just wasn't interested. And it was because these are professional practice conferences. These are not academic conferences. We're here to learn and go write code, not here to learn and go write papers. And from Alex's point of view, the conferences you should go to are academic conferences. So he has a very academic point of view, but he worked in industry. And I think the reason is they stripped him of his degrees. Now, I'll tell you this. If anybody tries to strip me of a degree I earned, I'm putting it on my resume anyway, because I earned it. But I think in the academic world, that doesn't fly, because they're going to contact your college and say, did he earn it? And they're going to say, no, he didn't. So anyway, his job at General Electric, he worked on a language that he created called Tecton, and it was a functional-based language. It was working on algorithms based on math, based on algebraic theories. And this was Alex who said it had no practical results. That's not my judgment. But one of the things that he learned from that is, he said, complexity assertions have to be part of the interface. And you need to realize that that was somewhat going against the tide at the time, because people then were talking about things like abstract base types and APIs and things like that, but they would consider the performance is on the implementation side. It's not part of the design. It's not part of the API design. And Alex had a very different point of view about that. So he did work, as I said, briefly. Briefly, in a college setting, he worked on a library of data structures and algorithms in Scheme, but then he was asked to do a generics library in Ada. And so he worked on that. He did do about a year, more or less a year, at Bell Labs. And he worked on a library of algorithms in C++. Now, this was long before the standard, but when Unix shipped, there was a collection of standard components that was part of Unix, selection of C++ components. And so part of that work was Alex's work. And he tried to convince Bjarne to add generics to C++, because at this time there was no templates in C++. Again, this is 1987, before the standard. But then he moved on to HP Labs. And he spent 4 years working on storage systems, meaning he basically learned everything there was to know about disk drives. But he was given a chance, while still at HP, in 1992, he was given a chance to do research. And they asked him to do generic programming in C++, because now C++ had templates. And so he then started on what would become the STL. The basis of it was started then. It wasn't called that then, but that's what it was. That's what he started on it. And his comments about templates in C++ is that Bjarne didn't do what he asked him to do. He wanted something that worked like generics and Ada. But Bjarne kind of went his own way about what he thought templates should be. And Alex's point of view was that that was very fortunate, because he said, I could do much more with C++ templates than I could with generics and Ada. So it was a compliment from him to Bjarne about his design there. Now, while still at HP, he had met, I should back up, he had met Andrew Koenig because they were both at Bell Labs. Andrew Koenig, for those of you who don't recognize the name, he was a very early C++ user. He wrote books of C++, and he was the chairman of the library standards committee of the standards committee. The library committee of the standards committee. He was chairman, and he and his wife, Barbara Moo, would come to Stanford every summer and teach a class at Stanford. And so in 1993, when he came, He met up with Alex because Alex was working at HP in the Bay Area. So they were in the Bay Area, they got together, and Alex said, hey, I'm working on C++ now, and I want to show you the library. And Andrew was very impressed. So impressed that he actually asked Alex to make a presentation to the Standards Committee later in the fall. Alex, and the slides to this are available. I'll tell you where in a little bit. But Alex said he thought the presentation was a little dry, but he thought it went over very well. But there was no discussion. This presentation was about thinking about types in a reasoning about types generally, and not about any particular library or generic programming. But then, in January, Andrew sent an email to Alex, and he said, if you're planning to make a submission of your library to the Standards Committee, the deadline was basically 19 days away. And Alex said, no, this doesn't make any sense. And here's why. He actually had a lot of reasons. One was, this would be the largest proposal the library committee, and maybe the entire Standards Committee would have seen up until that point. You have to understand that at this time, what had been standardized in the library was effectively three components. One was the C library. That's just by reference, we include everything in the C library. Another is the string class, and another was IO streams. And that was basically the standard library at the time. And you know what's in the STL, it's very large. And so he thought, the committee's gonna be overwhelmed by this submission. The other thing is that the committee was just about ready to ship. Now it turns out it wasn't gonna ship for 4 years, but software engineers don't do a good job of projecting how long it's gonna take to complete a task. That seems to be my observation. And so he thought, they're not going to be interested in something this big because they're trying to ship. And at the previous meeting, the committee had actually already voted not to accept any major proposals. So this isn't going to go over. But the other thing is, and the biggest thing probably was, he said, committee members aren't going to understand the library. Now, he wasn't saying this out of arrogance, that they weren't smart enough or something like that. No, what he was saying is that this being a research library, he's shown it to a lot of C++ programmers. And their response would be, well, that's pretty cool. I see how it works together. It's very logical, but I'm not sure how I would use it. Because at this time, remember, we're talking the mid-90s, everything was about object-oriented programming. C++ was the premier object-oriented programming language. And object-oriented programming was going to solve the problem of code reuse. So code reuse was this frustrating problem that people found out. People who were paying for software development would have an application built, and then they say, I've got another application in the same domain, so you should be able to reuse a lot of this code. And it turns out, not so much. That doesn't work so well. These functions are designed to work here, and they don't move very well. So people started writing libraries, and that helped a little with code reuse, but it still was very limited. And so object-oriented programming solved that, because we're not talking about functions, we're talking about objects. And once you make these objects, you can lift that object out of this application and drop it in another application. It just works. Wonderful. And so that was going to be the solution to code reuse. And that's what everybody was doing. And so when he showed his library to people, you can imagine what they thought about. It doesn't have virtual functions. It used standalone functions. Now, when Alex submitted it, these functions were all made member functions. And what he told me was he just thought there's no way the committee would accept them as standalone functions, because everybody was thinking in terms of encapsulation and members and all these things. Now, of course, the committee has figured out, and so these things are now standalone functions, which is what Alex thought they should be from the beginning. And it was also template-based. When I first started using C++, I contacted a friend of mine who had experience with C++, and I had a lot of respect for his opinion. I said, what do you think about C++? I've been hired to do this C++ project. And he said, it's a lot of great stuff. You'll love it. It's really good. There's only 2 things you have to stay away from: exceptions and templates. Now, why? Well, part of it was I think that the community as a whole didn't really understand exceptions and templates very well, but also there were tooling issues. Compilers weren't necessarily consistent about how they implemented things. There might have been performance issues, might have been, in the case of templates, code bloat kinds of things. So those are the things to stay away from. And a library that's going to be heavily template-based is something that most software engineers at the time, most C++ programmers at the time, would be a little bit pulled back. And I really want to emphasize how radical this was at the time. We are all used to using vector without even thinking about it. We understand that. But I was a contract programmer at the time. So this was back when software didn't get pushed out to the server every week. Instead, we put software on these little round things that went into boxes. That's how we made software. And that meant that a project would last for 9 months or a year. And as a software contractor, that's what I did. I would work on a project for 9 months and a year. And I would learn the framework, the object-oriented framework that I was working on. And I'd get really comfortable with that. And then if I went to the next project, if it used the same framework, great. But if it didn't, then I had to kind of start from scratch, learning what its ideas of what containers and things are. And so when I heard about the STL having been accepted in the standard, even though the standard wasn't shipping yet, I was excited. I wanted to get on board and learn about this because I knew it had these containers that I could use now in all my projects. So I started this tutorial. And the tutorial says, okay, here's what we're going to do. We're going to take this thing, and now we're going to put it into a vector with pushback. See, it's now in the vector. I said, no, it's not. It's still right here. A copy of it was in the vector. But, excuse me. But if you're comfortable with value semantics, you understand what that means. Yes, a copy of it's in the vector. But think about, from an object-oriented programming point of view, what are objects? Well, they're really base class pointers. So what does it mean to put an object in a container? Well, it means you copy in the base class pointer into something that's what we would think of as a vector of base class pointers, but you're also transferring ownership. So what that means is if you tell the container that you're closing the container, it's going to call delete on all the pointers that it owns. You can see how different a model this is than a value-based model. And so it really does, it's easy for us to ignore this now because we're so used to the STL, but this was really a radical way of thinking about things. Yeah, so it was really obvious that it didn't make sense for Alex to make a proposal out of this. And when he gave these reasons to Andrew, Andrew agreed. Andrew said, you're right. The committee is never going to accept your library if you don't submit it. So Alex and Ming Lee, who was working with him, worked 80-hour weeks and submitted the library. He gives a lot of credit to the people who helped him. Andrew was a big champion. Bjarne helped get it through. There were lots of people on the standards committee who helped get it through. But it was contentious. It was huge. And it was a different kind of paradigm. And for people who say what the standards committee's job is to standardize existing practice, this was not existing practice. This was a research library. So it's really a tribute to the beauty of the library that once the committee saw it, talked about it, they realized we can't ship a standard that doesn't have this library in it. It's an amazing achievement, just if you think about that. So Alex then moved on to Silicon Graphics because Silicon Graphics offered him an entire team to work on extending his now called STL library. He worked at Compaq, and it was while he was at Compaq, he met Sean Parent. And I refer you to the keynote that we had, the opening keynote about this, because Sean then hired him into Adobe, and they formed the Advanced Technology Group at Adobe. There's a lot of interesting story there, so you really need to get with Sean and get him at a bar and have him tell you all the stories. Very good. From Adobe, he went to A9, which is a subsidiary of Amazon. And that's important to me because that's where I got to meet Alex again. I had met him once because he went to a conference I was helping to organize. Who would expect that? He was a keynote speaker, and I got to introduce him. So I had met him, but this was an opportunity to work at the same company he was at. And when I talked to Sean, I actually talked to Sean, and I said, I'm a Mac programmer. Sean also has a history as a Mac programmer. And I said, Apple's getting away from C++. I want to go to a company that takes C++ seriously. And Sean said, well, A9 just hired Alex. They probably take C++ pretty seriously. So I contacted A9 and I talked to the recruiter and I told him, hey, I'm interested in this because Alex is there. And they actually, They actually arranged that when I went in to interview, Alex was there. He didn't sit in on the interview, but he just was there, met me again, and that was really great. And then while working at A9, I was able to go to classes at Alex. Alex had taught several classes at Adobe and also at A9, and that was really a privilege to be able to attend those classes. Excuse me. So Paul McJones, who is Alex's co-author on Elements of Programming, has put together Stepanov papers. If you go there, you will see obviously academic papers, but also the slide decks to the 2 sessions that Alex did at the committee. Those are interesting, and lots of other interviews, videos of him, talks, things like that. He wrote several books. I think the 2 most important are probably Elements of Programming and From Mathematics to Generic Programming. Elements of Programming breaks down programming in a very mathematical sense and builds it back up from there. Anyway, this is where you can find out more of his writings. And I'm not going to dig really deeply into generic programming, but I want to make certain we're all on board understanding what it is. It's a design methodology of programming, more than just design. It follows through with all of programming. But the idea is to supply algorithms in their most generic form. And as we discussed in the Sean's opening keynote, we don't invent these algorithms, we discover them. We look at existing code. We see how algorithms are implemented. But of course, they're not implemented generically, they're implemented in a specific situation. So we look at those code, we figure out what is the essence of this, and we develop it generically. It's very important that we honor the underlying machine model. That's how we maintain efficiency. Alex was once on a panel with people from other programming languages. And one of the things that Alex said on the panel, much to the delight of his other panelists, I'm sure, was the only languages worth really studying are C and C++. And his reasoning was, those are the languages that are based on how the machine works. There's no virtual machine, there's no abstraction about how we wish the machine worked because it made it easier to program. No. These languages are based on how the machine actually works. And so that's, again, Alex didn't want to just make beautiful code. He wanted to make code that would really be used to solve real world problems. And the last thing is, this is the real solution to code reuse. The problem that we ran into with object-oriented code reuse is, yes, you can take those objects you've created and you can pick them up and drop them into a completely different application that is completely different as long as it uses the same framework. And that's quite a limitation, it turns out. But we want to be able to reuse code by not having coupling in the code. We can pick up a container or an algorithm and use that in another application completely without ties to anything. This is where actual reuse happens. So one of Alex's mandates, which I touched on earlier, was that complexity assertions have to be part of the interface. So this is STD vector push front, but STD vector push front doesn't exist. Why not? Yeah.
Because it's ON complexity.
Right. Well, that's true. But the real answer is because it's not constant time.
Sure.
That's the idea, is that push front guarantees constant time. And Alex had said in an interview, imagine I make a stack class, which as you add things to it, slows down. That would just not be acceptable. It can be implemented better, so it should be implemented better. And so we want to put the performance guarantees, the complexity, in the API. We want to know that when I call push front or push back, that that's a constant time call. Or in the case of vector, an amortized constant time. So that was one of the things that he learned and pulled that into the STL. Notice this would be trivial to implement, right? It's not because pushback is hard to implement. You just call assert. It's straightforward. But again, as Brady just told us, assert's linear, not constant time. And so it's not appropriate. Another mandate of Alex is we don't do work and throw it away. Now, he didn't say we always return the work we do to the user. That's not what he said. He said we don't do work and throw it away. A slightly different meaning. And it drives design in some surprising ways. Now, here's an example where we are returning, or in this case, the way this is written, we're not returning the work. So what are we doing here? So this is a copy algorithm. It's not the correct interface for the copy algorithm. But what does it do? It takes two input iterators. These iterators are defining the range of elements that we're going to input. We start at the beginning of the range, and we end with the last element. No, we know better because we're used to it. That's what people would expect. A naive user using the library for the first time is going to expect that we have iterators to the first item and iterators to the last item. But that's not how the STL is designed. It points one past the last item. And I know for me, this is a little counterintuitive. Why is that? But when you use the STL, I'm constantly surprised at how often it comes up that, oh, that just works out. It's just exactly the right thing. So that's what we're going to do. Our input then is defined by this range. And then we have the output where we're going to copy 2. But notice that's not a pair. Why is that not a pair? Don't we need to know where the end is going to be? No, we're actually going to figure out where the end is going to be. Why? Because we're going to start at the beginning and we're going to copy however many elements there are in the input. And that tells us where the output is. So what's wrong with this interface?
Doesn't return the output iterator?
The caller can't tell where the output got to.
Exactly. It's very likely that if you're writing to some output, that you're going to want to write more stuff to that same output. Maybe this is written into a file, or maybe it's on a stream or something like that. And so once we have finished with this copy, we might want to copy other information or somehow maybe do a transform into some output. And so we need to know where that output, where did we end up? Where are we beginning our next output? Now, would that be hard to calculate? Perhaps not. We could do a distance on the inputs and then do an advance on the output and we could figure it out. And in many cases, that might be constant time, but it's still work that we're pushing on the user when we have already done the work. We know where the output is. So if we know where the output is, we want to return it, right? We don't do work and throw it away. Now, I want to talk about set theoretic algorithms. So who can tell me what the set theoretic algorithms are?
Like symmetric difference and things like that. The set algorithms?
Union, intersection.
Set intersection, right?
Set union.
Set union.
Difference.
Set difference. Symmetric difference.
Symmetric difference.
One more.
Power
Merge.
sets, maybe?
Merge?
Arguably, maybe, but that's not what I was thinking of. The other one is include. Does this set include this set? All right, so let's, these are the ones, right? Okay. Let's get away from code for just a second and talk about sets from a mathematical point of view. Does a set need to be sorted? I'm going to give you an exercise here. I want you to give me the intersection of the following two sets. I have apple, banana, pear, and banana. What's the intersection?
Pear and banana.
Pear and banana. Did you have to sort them to figure that out?
No.
It's not even clear how you would sort fruit, right?
Right.
Right? So from a strictly mathematical point of view, there's no reason that our input has to be sorted. But let me now ask you this, now thinking about code. Suppose I were to ask you, we're going to implement, thank you, we're going to implement set intersection. And I'm going to guarantee that the inputs are sorted. Could you do that? It's not a workshop. You don't actually have to do it. We're just going to think through it, right? Is this hard to do?
Yeah.
Right. You just start at the beginning. If they're the same, that's the intersection. We write out whichever one is the lesser. We advance, check again, repeat till we get to the end. What's the order of that operation?
Order in.
Order in. Right. Linear operation. Great. Okay. Now we want to do this where there's no guarantee that the input's sorted. Now what do we do?
Now it's much trickier.
What's that?
It's O n squared.
Well,
We might be able to do better.
But
But it's no longer linear. That's one thing, right?
you can build a hash table on one and iterate over the other.
Yes.
That's linear.
Yeah, you could do a hash. The easy answer is just say, well, let's just sort it first, right? There's some problems with that. If we actually had an algorithm and said, oh, you're going to pass your data in, and as a side effect of getting the output, we're also going to modify. No, we're not doing that. We don't want to have those kind of side effects, right? The other problem is we could do something like, well, we're not actually going to move the data, because the other thing about that is someone couldn't pass in const data and do an intersection on it if we said, oh, we're going to. But you could build an index, right? You could create something like a vector with iterators, or you could create a hash table, something like that. You could do that, but this violates Alex's mandate. We're not going to do work and throw it away. And that would be doing work that would then be thrown away. So the way that Alex approached this was, he wasn't saying that the input ranges have to be sorted to make his job easier as an implementer. That's not what he was doing. What he was saying is that, because it wouldn't be difficult to do this, but for set theoretic operations, Alex was saying, I'm not going to build a hash table or an index or something like that and throw it away. Instead, I'm going to push it back on the caller and say the caller has to sort the data. Now, what does this do? Well, for one thing, it's possible the data is already sorted, right? Imagine if you had sorted data already and you pass it into an algorithm which builds an index to sort the data. What a waste that would be, right? But also, once the caller has done the work to sort the data, again, the library has a sort routine. It's not hard to do that. But once the caller has sorted the data, they can call other set theoretic operations. They can call binary search. There's lots of advantages to them of having sorted data. But the main driver for this decision was Alex's mandate. We don't do work and throw it away. And so if we have to change the algorithm in some way so that it's not doing work and throwing it away by changing the requirements, we will do that. But we're not going to do work and throw it away. So if you talk to a mathematician friend and say, oh, in C++, we have this data structure called a set. The mathematician says, yeah, that's a good idea. That's going to be useful. And then you say, and it keeps things ordered. And your mathematician friend, whoa, what? Sets don't have to be ordered. In fact, it's not even clear that sets need to be orderable. They not necessarily be sortable. But what Alex, of course, knew this. He was a mathematician. He understood sets very well. But what he was also know was that from a practical point of view, if you want to do anything with sets, they need to be ordered. And so a container that maintains orders and doesn't have duplicates is a perfect for implementing sets. And that's why we have set, right? Now, if you really want to blow the mind of your mathematician friends, tell them about multiset. Because a mathematician knows that something's either in the set or it's not in the set. It can't be in the set twice, right? But again, from Alex's practical point of view, there are problems we need to solve where sometimes there will be duplicates. And so that's why we have multi-set and multi-map. Okay. All right, now I want to talk about binary search. I mentioned that earlier. What algorithms in the standard library use binary search?
Lower bound,
Lower bound,
upper bound,
binary search,
partition point.
Partition point. Oh, that's the one nobody remembers, right? Okay, you missed one. What are these together?
Equal range.
Equal range, okay. Equal range and partition point. So what is partition point? Well, partition is an algorithm that I think people are tempted to say it sorts. It doesn't sort, it reorders. It's a mutable algorithm. You give it a range of data, and it mutates the order in such a way that you also give it a predicate. What's a predicate? Predicate's just anything you can call that returns a Boolean or something convertible to Boolean if you're a C++ programmer. And what we do is the algorithm will evaluate the predicate on all the elements and make certain that with this reordering, all the elements for which the predicate returns true precede all the elements for which the predicate returns false. And because we don't throw away work, what do we return from that? From partition. What is it we return? The partition point, exactly. And what is the partition point? Is it the last element that returns true? No, it's one past. And notice again, this is the beauty. Because suppose the reason I partitioned all my elements is because I've done a quality check on them. And some of them may be ready for shipping. So which ones do I want? Well, I want from begin to partition point. Let's ship those. But maybe what I need is the ones that didn't pass because they have to be reworked so they will pass. So what is that? Well, that's from partition point to end. And notice, I don't have to make any adjustments. I don't have to add one or anything. That partition point is this beautiful demarcation of where one range ends and where another range begins. And the algorithm called partition point is what you use if you have data that you know is partitioned. It has to be part of the input requirement. And you want to know what is the partition point. Now, this would be trivial to implement by just doing a linear search. You would look for the first element doesn't return true. But that's not as efficient as it could be because we could use binary search. And what is the performance of binary search? It's logarithmic, right? Okay, so these were not all in the original proposal. The original proposal only had lower bound, upper bound, and equal range. He hadn't quite got around to partition point yet. But he also didn't have binary search in there. But notice, these all have something in common. And that is what they return. They return iterators. Equal range returns a pair of iterators. But they return the position that we're looking for. So lower bound is returning the position that is the first position a particular value could appear at. And upper bound is one past the last position where a particular value could appear at. But notice, we don't return whether the value is in the range or not. We only return the position. Why is that? The reason is that's the work. The work we're doing is finding the position. Figuring out whether or not a particular value is there, that's a constant time. That's trivial. It's figuring out where it is. That's where the work is. That's where you could have an off by one error in your loop or something like that. So that's why we have the algorithm. And when Alex made his submission and the committee was debating it, Bjarne came to Alex and said, we need to add binary search to your algorithm library. And Alex said, no, we don't need that. We've got it covered. And Bjarne said, no, we need to add binary search to the algorithm library. And Alex said, no, we've got lower bound, upper bound, equal range. We've got it covered. We don't need to add that. And Bjarne said, you don't understand. Here's what's going on. We have a lot of C++ programmers on the committee and some off the committee. They're looking at your proposal because it's so important, a proposal. And when they get to the section on algorithms, they're looking for binary search. He said, some software engineers know lots of algorithms, but all software engineers know at least one. They know binary search. And so that's the one they look for. And they don't see it there. And therefore, they think your library is not very impressive because you don't have the algorithm that they know about. And Alex said, okay, well, what would it do? And Bjarne said, it doesn't matter what it does. We just need to add it. So what does binary search return? What is binary search? What does it do? What?
Bool.
It returns a bool. It tells you whether or not the value that you're looking for is in the range. And it does it in logarithmic time. Now, this reminds me of my wife. When I ask her, I say, have you seen my keys? And she says, yes. So this turns out to be less useful than you can imagine. And in fact, when I was at A9, there was a meeting where we were talking about algorithms generally, and Alex made the point. He said, binary search, useless. Nobody will ever use that. They'll always use lower bound instead. And I said, well, Alex, there's one place in our search engine code where I need to know if a particular item is in the cache. If it's not in the cache, I'm not going to add it. And if it is in the cache, I'm not going to remove it. I just need to know, is it in the cache? I don't even know why I needed to know that, but that's what I need to know. And I used binary search for that. Now, I could have used lower bound. Why didn't I? Well, as I said, lower bound, to determine if a value is at the lower bound, we do a constant time. But it's not a single test. We have to do two tests. Why?
You have to check it wasn't the end.
You have to be certain that the position is not the end position. If it's the end position, we can't legally dereference it. So first we have to check if it's in, and then we can dereference it and compare the value we're looking for. So if what you need to know is it there, you can use binary search if that's the only thing you need to know. But I completely agree with Alex. This is much, much less useful than lower bound. So that was Alex's mandate. We don't do work and throw it away. And this has some kind of surprising design implications. So, as I mentioned, Sean hired Alex. And at this point, if you're watching on the video, you need to pause this video, go to YouTube, do a search on Sean Parent, and then you should only watch the good videos. So you can come back in about 2.5 weeks, right? So Sean gave a talk called C++ Seasoning. And in it, he said he used no raw loops. And what did he mean by that? We have to use loops, we're processing data after all. And data is plural, right? It's ranges of information. We have to loop through it to process it. But what Sean was saying is if you look at his code, you'll see code that is linear, and where you might expect to see a loop, instead he calls an algorithm. Because what is an algorithm? It's an encapsulation of a loop. We've taken that loop logic and we've isolated it. And why did we do that? Well, we did it so that we can think deeply about what it is we're trying to do, document it carefully, and independently test it. So when we drop it in our code, we have high confidence that it's doing exactly what it is. So when someone reads our code or reviews our code, they don't have to stare at that loop and see, is there a off by one error in there? Are we maybe freeing something we shouldn't free? Is there an issue? No, because we have created the algorithm separately. Now, one of the things that Sean talks about is that sometimes it's difficult. It's not always obvious when you look at a loop to say, oh, that's a rotate. Sometimes it's hard to know which algorithm this is. But you can search and find, what is this algorithm? Think deeply about the algorithm and figure out what algorithm it is. And if it's not there, then, as Sean told us, then you're lucky because you get to create a whole new algorithm, which you can add to your personal collection of algorithms or the project's collection of algorithms or your company's collection of algorithms. And if it's really good, we can get it into Boost or into the standard and share it with the world. But this is the discipline that I've adopted, and I love it. It is more work because you spend a lot of time on those loops, but once you get that loop right, your code is really easy to follow, really easy to understand. So that is the power of encapsulating loops into generic algorithms. So the STL is made up of essentially 4 components. From Alex's point of view, the important thing is the algorithm. Now, I don't think we emphasize this enough. And as I said, the reason I was interested in the STL myself was because, it has all these cool containers. Well, containers are just an implementation detail from Alex's point of view. Why do containers even exist? Well, as I said, algorithms work on data. The data has to be somewhere. So we need to have containers. But we don't want to couple the algorithm to the container. So we have something called an iterator. And the iterator is a magic bridge. On one end, it's very generic. It has the same API as a pointer. You want information, you dereference. You want the next piece of information, you increment. If it's a random access iterator, you can do pointer math on it. It's just a magic pointer. That's all it is. But on the other end, it's not generic at all. It may know detailed information about a container so that it knows how to traverse that container as efficiently as possible. Okay? So those are the important things, but Alex would emphasize the algorithm is the most important thing. And then there's the callables. So what are the callables for? Well, the callables are to allow our algorithms to become just a little bit more generic. So one of the algorithms that is in the library is find. And what find does is it does a linear search looking for a particular value that you've supplied. But that's not very generic because although that's very common, so it justifies why we would have that algorithm, but the thing is we may not want to find something that's just equal to something. We may want to find something that's between 2 values. So we could write a function called find if between. And then you supply the 2 values and it returns the first item between those ranges. Or we could say something that's find greater and give it a minimum value. But of course, those are just redundant and useless if we can encapsulate the criterion that we're looking for into a function, into a predicate, right? And so that's what the callables are. It allows us to take algorithms and make them yet more generic by putting some logic that we're providing to be used by the algorithm appropriately. And then the other important thing to know about the STL, and from my point of view, the most important thing to understand is that the STL is held together by conventions. So containers represent a sequence of values. You could imagine a container that is a row column container. To find an item, you have to provide the row and the column. Well, that's not going to work with the STL. You'd have to write a wrapper on that that's either column-based or row-based, because our concept of a container is that it represents a single sequence of values. Now, that works for most containers. For the containers it doesn't, it's probably trivial to make that kind of adaptation. The containers provide iterators with specific names like begin and end. This is arbitrary. Begin and end can be spelled very differently. but this is the convention that we follow. Algorithms use iterators to define the ranges that they're going to work on, and these are specified with half-open ranges, meaning the beginning and one past the end. Again, that's just a convention. Turns out that convention works very well, as I mentioned earlier, but the STL could have been designed differently. These are just conventions. But the power of the convention is that that's what allows the code reuse. If we follow the conventions, we can add new containers. And they just work with all the existing STL. We can add new algorithms. I think you'll probably add more algorithms than you will containers. But notice, I may be working on a container, Ben's working on an algorithm, and Aaron can use both of our products. Ben didn't know about my container. I didn't know about his algorithm, but Aaron is able to confidently use both together. That's what the code reuse is about. And it's just because we're following the conventions. One thing you could add is new iterators. Now, this is sometimes a surprise to new students because they'll say, wait a minute, iterators come with the containers, right? I have a vector iterator, it comes with vector. But it turns out that you can, in fact, add power to our algorithms by saying, this range that you're looking at, I don't want you to look at every element, I only want to look at certain elements. So you could create, for example, a filter iterator. So what's a filter iterator? Well, all of our iterator adapters will have the pattern that they have a container iterator that they are built around. So for a filter iterator, you have the container iterator, the base iterator, and a predicate. And so with our iterator, then when you say plus plus, what our adapter does is it says plus plus on the container iterator or the contained iterator, and then runs it with the predicate to see if we have found a new item that satisfies the filter. If we have, we stop. If not, we do another plus plus and repeat. Now, it's a little more complicated than that. You have to make sure you don't run off the end. But basically what you've done is you've now allowed an algorithm to work on items in a container, but only selected ones. And so that, again, it's a new toolbox. And once you've created that filter iterator, it works just as well with any container. You're just wrapping because you've made it a template and it can wrap any kind of container or any kind of iterator. And then, of course, function objects, which we almost always use lambdas for, as Ray talked about earlier. You can do all these wonderful, amazing things with lambda expressions. But the point is, there's no required base class. There's no virtual functions to overload. You follow the conventions and you're in. You using the STL is extending the STL. And that's the power of it. And that's what gives us our code reuse. So it's been about 30 years since the STL was submitted. And I think it's had a huge impact. You can watch Sean's keynote to see some of the impact. But I think it's made it amazing. It's certainly changed the way I think about code. I think it's had huge impacts, not just in the C++ world, but more broadly. But I'm going to talk about some lessons learned. Again, these are places where I think the STL is less than perfect. And again, most of these things were pointed out by Alex himself. So the first one is the name vector. So what's wrong with the name vector?
It's not a mathematical
vector.
Right. It's a name collision with the mathematical concept of a vector, which is what? A magnitude and a direction. Right? Magnitude and direction is a vector. And in fact, that's kind of where the idea that an allocated array comes from, because you can keep adding at the end. So it grows in one direction. So that was kind of why the name came from. Kevin Carpenter told me he's doing some research on early submissions to the committee. And there was one that predated Alex's submission that used the term vector to describe an allocated array. So this is one of the things that Alex himself said. I was told that what I was describing was a vector and that's what I should call it. But he said he didn't like the name, but he didn't have a better name. Here's what I would have proposed, AA. I think it says it's an allocated array. Now, well, that's really short. That's a little cryptic. But notice, this is the most common container we use. It would have been really easy to adapt to that. And I think having a short name for that makes a lot of sense. But of course, absolutely I'm not proposing we change it. Please don't misquote me saying I'm telling the committee they need to change the name of vector. That's a complete non-starter. Another issue is the difference between a command and an attribute. Now, I'm sure everyone in this room, if I ask you if clear or empty were a command or an attribute, you can tell me. But the problem is, to someone using the library for the first time, it's not clear which of these is a command and which is an attribute. And it would have been so trivial to fix this by just saying that the attributes should be, if it's a predicate, it should indicate that it's a predicate. So saying is empty. Now, we kind of have solutions to this now, or partial solutions maybe. As of C++ 17, we can say no discard on the return value. And as of 20, we can even say no discard and explain what the problem is. Where would we use this?
Empty.
On empty, right. Because the idea is if you call empty and you don't check the return value, you're expecting empty to do something it's not going to do, right? And so we can detect that at compile time, which is great. Okay. What is the sort order? There's a default sort order in the STL. What is it?
Less than.
Less.
Operator less.
Right, it's less. And that gives us an ascending sort. And I did ask Alex, why did you pick this? And he said, well, you want some default because that is convenient for programmers. And if you happen to be working with characters or strings, then this gives you alphabetic sort, right? So that's why he picked what he picked. Okay, so that's the reason. But the STL doesn't follow this everywhere. It does it in the obvious places, but there's a couple of not so obvious places. And one is partition. And we talked about partition. What does it do? Well, it reorders and it puts all the predicate true results before all the predicate false results. But true or false, which is less? The false is less. So arguably the falses should come before the trues. And Alex kind of discovered this when he was working with the algorithm library himself and trying to build up things that did sorting, and he was using a partition at one point and realized, oh, it's kind of the opposite of what I want. I have to negate my predicate to get the actual behavior I want. The other one is in max. So what does max do? Well, we have min and max, and given two values, they return the iterator to the one that is either the min or the max. But that opens the question, what do you do if they're equal? Well, the standard just says, and this was Alex's decision, we just return the first one. If they're equal, we return the first one. Well, that makes a lot of sense for min, because if you're trying to maintain a sort order, and you look at two items and say, which one is the minimum? Because I want it to be in the first position. So if the second one is the minimum, I have to reverse and I have to do a swap. That's great, because if they happen to be equal, then I don't have to swap, and it tells me the first one is the minimum. That's great. But what if I did the same thing for max? Well, I want to swap them if the first one is the max. But if they happen to be equal, I'm still going to do a swap that I don't need to do. And again, this bit Alex as he was trying to build up some algorithms on these lower level algorithms. And he just pointed out himself, these are kind of inconsistent. Now, again, I'm not saying the committee should change these. That would be disastrous. But it's just something that we learn from. We think about things, we try to be consistent. So the standard has a couple of unordered multis, unordered multiset, unordered multimap. So how are the unordered containers implemented?
Hash.
They're hash tables, right? Okay. Do they have to be? Does the standard say they have to be hashes?
Yes.
More or less.
Well, the parameters include the hash function. So I think pretty much it has to be a hash table, right? But the question is, why don't we just call them hash something? Why do we call them unordered? It's longer, it's a mouthful, and it kind of obscures what we're actually doing here. So why don't we call it hash? Well, it turns out that this comes from the fact that when the standards committee was evaluating Alex's proposal, when they got to the tree-based containers, that is set and map and multi-map and multi-set, those were really easy to standardize. If you have a comparator, that's all you need. Doesn't matter. There's no weird situation where you need to think about performance. No, if you have a comparator, it's going to give you logarithmic performance. Everything's good. But when you get to hash tables, well, now we have to think about bucket strategies. We have to think about hash functions. Do we want to be able to iterate over specific buckets? What's the API for that? And of course, when engineers have decisions to make, they contemplate that a lot. And so what was happening in the committee itself, they looked at the tree-based containers, yeah, that was straightforward. But then when they got to the hash stuff, oh no, there was lots of rabbit holing about what should we do, what's the best way to do this. And so someone came up with a compromise. They said, look, let's ship the tree-based containers now. And because we're trying to ship a standard, let's ship the hash-based containers with the next version of the standard. That'll probably be 2-3 years from now, right? Nobody knew it was going to be 13 years, but it was a compromise that people could live with. So that's what they did. They said the first release, we're going to have set and map, but we're not going to have hash set and hash map. But notice who attends committee meetings. Well, lots of people do, but that includes implementers. And we love implementers. Compiler writers, library writers, we want them there. We want their valuable input, their experience, keeping us honest. But all of them knew about Alex's proposal, and they knew about the compromise. So nobody ever said, hash, is that really important? We don't want? Nobody said that. Hashes were clearly coming. And we knew what Alex had in mind for them. And so every single library implementer shipped hash set, hash map. All of them did. And I think it was the right thing to do. They knew it was coming, and why not give users the ability to use those right away? The problem was, every single one of them, other than my other idol, Howard Hinnett, shipped them in the STD namespace. Howard, who was working at MetroWorks at the time, he shipped it in the MetroWorks namespace. So he gave you the ability to use hashes if you wanted, but he respected that they weren't part of the standard yet. So what happened when the committee met and said, okay, now we're going to do the hash tables. We were going to do those. And then they realized, oh no, if we ship the API that Microsoft ships, we're going to upset all the GNU people. And if we ship the API that GNU ships, then we're going to upset all the Microsoft people. And if we do what we really want, which is design the API we think it should be, then we're going to upset everybody. So what did they do? Instead of using the word hash, they used the word unordered. Now, I try as much as I can to spread the rumor that the real reason they didn't use hash was because this was in the mid-90s and the Standards Committee was very, very concerned about drug use in American youth. No. So that's why it's called unordered. All right, why do we want hash? They're so complicated. Why do we want? It's because the best case gives us outstanding performance. Constant time lookup. That's just amazing. But I said best case. Why do we not always get best case? What's the problem?
Exception guarantees.
Collisions.
What'd you say?
Collisions?
Collisions, exactly. Collisions. So really quick, probably everybody here knows how to do a hash table, but let's just talk about it. What we have is we have a key that we want to look at. Yeah, Eduardo?
Just quick question. I believe that one of the reasons for why hash wasn't approved or properly designed or completely designed back in the standardization process is that it is not clear what is the best mechanism for hashing.
Well, we have definitely learned that since. And maybe there were people in the Standards Committee at the time that felt that way, but I don't think that was the general thought. I think they felt that what Alex had was good enough. And so they were just arguing about the API. And there are guarantees that fall in line. We're going to talk a little bit later about node-based containers. And one of the things about node-based containers is once you put something into a node, into a container, it never changes, never moves. It's always at that same location. It's very stable. Vector doesn't do that. Deck doesn't do that. If you add or remove things before an item, it gets moved. But in the node-based containers, there's a node per element, and so it has its own memory, so it never moves. As long as the item's in the container, it's at the same address. That's very stable. And that's the kind of thing that I think some people would say, maybe that's not the best approach for hash, but it was consistent with all the other node-based containers. So I think there may have been some compromises that were accepted because they thought it made sense for the library. I'm not sure. I wasn't involved in the debate. I can't tell you. What I can tell you is the delay was caused because it was a more complicated API. And then they came back and they standardized an API in unordered that they felt was okay at the time, obviously. But I think since then, there's a lot of belief that we could have done better or we should do better now. I mean, it's very open how we could do better hashing. But I don't think that was the issue here. And so getting back to the collisions, how can we, I'm going to talk briefly. We have a key, we have a hash function. What is a hash function? It's simply a function that can take whatever the key is and convert it into an integer. That's all it is. It just converts it to an integer. And then within our container, we have some number of buckets. And what we do is we mod this integer number with the number of buckets, and that tells us what bucket the item's in. So we do a constant time. We do the hash function, and they know, boom, it's this bucket. But the problem is we may have collisions, meaning we may have multiple items in the same bucket. And so what happens is we go from constant time to the bucket to maybe linear time, or if we want to spend the time, maybe we could keep it sorted and do a binary search. But it's more expensive to get to the item if there are collisions. So hash tables are amazingly optimal when there's never a collision. But unfortunately, in the real world, we have collisions. So what are the sources of these collisions? Well, one possible source is that if you have two different keys, they could hash to the same integer, right? I'm sorry, not to the same integer, but to an integer that when modded gives you the same bucket. Does that make sense? So this key mods to the value of 12. This key mods to the value of 22. We have 10 buckets. They end up in the same bucket. So how would you fix this? What do we do to prevent this collision? Remember, we want to minimize collisions because that's where our performance is.
More buckets.
More buckets.
More buckets. Very simple. Little trade-off, a little more memory for much better performance. Real easy. But now, suppose you have different keys that hash to the same exact value. Now it doesn't matter how many buckets you have. They're going to end up in the same bucket. How do we fix this?
Better hash
function.
Better hash function. That, of course, is a graduate paper by itself, right? It's not a trivial thing to do. But the answer is easy. We need a better hash function somehow. But there's one other way we could get a collision, and that is if the keys themselves are duplicates. If the keys are duplicates, it doesn't matter what your hash function is. It'll always give you the same answer. It better, or the hash table's not going to work at all. So we now have the different keys that happen to generate the same hash value and therefore generate into the same bucket. And the fix for that is, there is no fix for that. If you have duplicate keys, you are compromising your performance. And it just has unacceptable performance. This is my opinion that Alex should not have made unordered, or in his case, hash set, hash multi-set, hash multi-map. He shouldn't have done it. The committee shouldn't have standardized it. This is just poison to performance. And if I were reviewing your code, then that would be an instant red flag to me. Any questions about that? Yeah, Eduardo.
Yeah, precisely. I'm sorry to disagree with you that we know what is the best way to do hashing. I think that in your audience, there are people who have implemented hashing tables, and they probably agree that it is not very clear what is the best. So I think that historically, our community has made the mistake of settling for one size fits all instead of articulating how to express different choices for something that doesn't have a clear best. That's one of the things that I mentioned yesterday. And in particular, our community has not fixed fundamental errors in the view or vision of Stepanov from 30 years ago. And it's not his fault, it is our fault that we haven't learned from the experience of using these things. Like, for example, a set is not a set. A set is a map between a key and the rest of the object. That we have chosen that an in-place mapping is good enough for most cases is entirely different to the fact that it continues to be a set. Continues to be a map. And therefore you have that abomination of multi-set that it is a map between a key and a collection of elements that share the key. So I think that the thing that I find that is dissatisfying is that our community didn't improve upon the design of the standard template library in 30 years.
So I disagree with your initial premise because I don't think I said that we know best how to do hashing. And if I did say that, it was a slip of the tongue. I certainly don't mean we have that nailed yet. I strongly believe that the solution to what you're implying is to continue to add containers, and I think they should go into Boost rather than the standard, because once they're in the standard, they're hard to change. And so, but anyway, it's not what I'm trying to argue here. It's very clear to me that the importance of the STL is not the individual containers or even individual specific algorithms, but instead it's the standard, the conventions. And those conventions are not in any way impacted by the issues you're raising, which are all totally valid. I'm totally on deck with it. You have another comment?
Yeah, the other comment is that it is not that I think that we have to have a plethora of different implementations, but we have to realize that we are putting together too many things that result in a one-size-fits-all, and we have to stop doing that. Like, for example, there is a template adapter, which is a cube, okay, which reflects we can use a substrate to do a cube that, a stack, the template adapter of a stack. We can do a stack with a double-ended queue or with a vector, etc., right? So we have separated those things into better concepts. And I don't see happening that there is criticism of some design mistakes in the standard template library that we can fix, but yet what we do is to continue using them.
So I don't disagree with any of that, but we're not solving that here. That's not what we're talking about here. I am on board with your direction there, absolutely. But that's not the point I'm trying to make. All right. One day when I was talking to Alex, he said, seemed to me kind of out of the blue, he said, well, the STL is out of date. And I was shocked. I was like, wait a minute. I'm changing my career to be teaching people how to use the STL, and you're telling me it's out of date? What? And then I don't even understand how it could be out of date. These conventions make sense. There's nothing date specific about the conventions. But what he was actually saying is he was talking about the containers. He says the containers were designed for systems in the 1990s. And he was telling me this, well, I guess it's over a decade ago now, but it was decades after the 1990s. So how have systems changed since the 1990s? Well, one of the things he pointed out was malloc is more expensive. Now, of course, he meant relatively more expensive. Our computers are so much faster than the 1990s computers that, of course, malloc is faster. But what he meant was malloc is relatively more expensive. Why is that?
More cores.
More cores?
So like synchronization is more expensive?
Right, it's the threading. Very often in my classes when I ask this question, they'll say it's because we have so much more memory. Well, malloc is designed to scale. It's not the amount of memory. It's the fact that in a multi-threaded application, the first thing we have to do is take a lock because malloc's not reentrant. And most of the time in the 1990s, now there were multi-threaded applications in the 1990s, but almost all applications were simply single-threaded. Today, that's changing. We are using more and more multi-threaded. But in the 1990s, we just took it for granted that malloc didn't need to be reentrant because we didn't have threads. Now we have threads. That makes malloc more expensive. And the other thing was all memory accesses have the same cost. Now, what is he talking about there? Caching, absolutely, caching. So when we launched CPPCon in 2014, I was pretty confident that our program was going to be really, really appreciated by the attendees. But of course, I was nervous. And so I was hanging out in the corridor waiting for people to leave the sessions. And I wanted to see on their faces, were they delighted, were they excited, all these things. And in the afternoon of the first day, I overheard someone coming out of a session who said, I get it already. It's all about caches. Well, apparently he'd sat into 3 separate sessions where the speaker had talked about the cost of a cache hit versus a cost miss. And it's truly mind-blowing. And so we're very, very aware of this now. Now, there might have been some cache situations in the 1990s, but we just didn't worry about it. We didn't think about it. It wasn't driving our designs the way it is today. So what's the impact on this? What does this mean for the containers we have? Well, the implication for containers, we want to reduce the calls to malloc and keep data local, right? Okay, so what are the implications for node-based containers? Node-based containers, as we said, call malloc for every single item. And because we're calling malloc for every single item, it's possible that 2 items could be very close and therefore in the same cache, but it's much more likely that they're going to be scattered everywhere. So what does this say then on the flip side? What does this say about vector, which is shares malloc among lots and lots of items, and things are crammed together as tightly as possible, and so they're likely to be in the same cache lines, right? Okay, so this is from Design and Evolution of C++ that Bjarne wrote in the mid-90s when we were talking about this, and he said that the vector should be your default container. What Alex said was, if you can solve your problem with vector, you should use vector. If you can't, you should restate the problem so that you can solve the problem with vector. Now, of course, Alex had implemented all of the containers, right? He was well aware of the strengths and weaknesses of all the containers, and he said, yes, you should use vector, right? Now, that was the decision that they made in the 1990s. How much more important is that today when we have these other effects that make vector even more appealing versus node-based containers? Now, what conclusions can we draw from this? Well, one is, yes, you should be using vector. Maybe we should think about B-tree or other containers. B-tree is this interesting hybrid where it's kind of like a node-based containers has some of the advantages of node-based containers, but it has short buffers with multiple items in it, so there's fewer mallocs per item. I believe Google has an open source implementation of B-tree. I don't know that the committee has ever looked at B-tree, so I don't know if there's a paper for that. But anyway, that again is, and I think the interesting thing, again, from my point of view, is that doesn't make the STL out of date. That makes the original containers potentially out of date. And that's one of the things that Eduardo was pointing out, is we could probably do better on some of those containers. All right, I want to ask a different question then. And that is, what is the STL? This was actually Scott Meyer's question. And Scott had a number of possible answers. He said it could be the portion of the standard library concerning containers, algorithms, and related functionality. He could say it's that plus strings or that plus IO streams. Now, the history again, as I told you, strings and IO streams were in the standard before the STL proposal. But wait a minute, doesn't the string class have begin and end? What an amazing coincidence that they anticipated the, no, of course. They went back and changed the definitions of the strings and IO streams to make them STL friendly, right? But they were not actually part of the original STL. But Scott's saying, well, some people could lump them in and think of them as part of the STL. Or you might even think of some things that actually aren't in the standard, but are from some other sources that were extending the STL. And Scott also said some people might answer the entire C++ library, the standard library. And Scott says this is just wrong. I completely agree with Scott on this. But I have definitely heard people in talking, you can tell from context that when they mean the standard library, they just say the STL. They're including everything. Yeah, Brady.
Do you know what the name of the MSVC standard library is?
No.
It's STL.
Oh, okay. All right.
But do you know the name that may have come from?
I'm not saying it's right or wrong.
Speaking of names, I was gonna mention when I was talking about Andrew Koenig, I was gonna mention that Andrew Koenig, as far as I know, is the only person who had his name in the standard. There was something called Koenig lookup. It's now been renamed argument dependent lookup. But he actually got his name in the standard because he proposed that lookup. And people didn't know how to describe it, so they just called it Koenig lookup. Anyway, so Scott and I agree on this. What?
Neeploids.
Yeah, Eric Neeploid got his name in.
Okay, there you go. All right. Okay, so here's Scott's answer. Scott says, anything in the standard C++ library that supports iterators, that is containers, strings, algorithms, some aspects of IO streams. And he points out that this would also then include anything that's been added to it, even regular expressions. We don't really think of them as part of the STL, but they do have iterators for iterating over matches. My definition is much more inclusive. What I say is, if you're following the STL conventions, that's part of the STL. So I don't care if it's been in the standard. I don't care if you've even checked it into GitHub yet. If you're following the conventions, that's the STL. That's my opinion on what the STL is. And the reason I am talking about how to use the STL, how to extend the STL, is because I believe this is how you become a better C++ programmer. You use the STL better. And the way you use the STL better is to understand what its purpose is, understand the direction, and understand how to extend it and make your code easier to read, more robust, more consistent. And that's my thoughts. Anybody have questions? No, thank you. Yes.
One question. So about the choice of vector as being default container. So I have some thinking. Like it feels to me, is the vector should be the default choice? Imagine beginner. He has no idea what the best algorithm for his problem is going to be. Is a vector better than hash table in that case? What should we be prioritizing here? Is that like vector has better performance, if you know how to use it well, but may like have more rough edges for beginners, right?
Well, I think that saying default implies there are alternatives that are better fit in certain specifics. And I think what we have to teach people is these are where these trade-offs make a difference, right? As you scale up, doing linear finds on a vector can be much more expensive than, that's why we accept the complications of a hash table. On the other hand, if you're writing an application, I have to have a little container that's going to contain, a couple dozen items, well, perhaps the hash table is overkill for that. One of the things that Alex once remarked about was how easy it is to do something using the STL that's something like, oh, I've created a linked list of hash tables with trees in them. And that's really easy to do with the STL. And from Alex's point of view, that's just a horrific design. It's just really complicated, right? And so, yeah, I think vector is amazing. It just works so well. One of Alex's classes at A9, he talked about Fortran, and he talked about the container in Fortran isn't an array, and it's just so amazingly efficient, right? But there are reasons that people didn't come up with hash tables because they thought, oh, it would really be fun to make up hash tables and think about buckets. No, they did it because there are trade-offs. There are times when a hash table is a better fit. So I think we need to educate people about that. And I don't think saying that vector is the default means that if you use something else, you've made the wrong choice. So, yeah, any other questions? All right, well, go ahead.
A common performance bug that I see fixed at work is people will replace a std unordered map with a value, like a hash map where you don't have to jump to the value, like instead of node, it's using value. And like it's a very common use case where you construct a map at the beginning of the process, and then it's read only, and you're never invalidating iterators, so you're not losing anything that way. And I wonder why that never got added to the standard.
I think it is. It's a flat map, right?
Yeah. Okay.
A flat map is effectively, it has the map API, but the backing store, instead of being a tree, is a vector. And so you can do binary searches on it. And
O of one lookup, please.
Doing it as a back for the hash. So like a flat hash.
I'm saying instead of storing pointers, you're just storing maybe your struct is only 12 bytes, right? And so like there can below a certain size, instead of storing pointers, you can just store the value directly and avoid jump.
You're talking about open addressing versus closed addressing.
Yeah.
Right?
It's because reference stability is the thing that we never got everyone to agree we didn't need.
Right, I'm saying that there are cases where you don't need reference stability, and
Most cases.
the STL doesn't give
Right.
you a container that can exploit that.
Well,
why not?
talk to Eduardo and tell him what you want your container to be, and then get it into Boost. I would never say that the set of containers that Alex, in fact, I told you 2 of his containers you shouldn't use. A mistake. And certainly of the others, you could imagine better ones, right? Again, the brilliance of the STL was not so much the individual, those are just implementation decisions, right? The brilliance of the STL was thinking about generic programming in a general way and coming up with conventions that allowed us to reuse code and allow us then to replace. So if somebody is using a hash table which has reference stability and they don't need that, and a better implementation of a hash table can be created, just drop it in because it'll work. Why? Because we follow the conventions of begin and end and all these other things, right? Yeah.
Yeah. So another thing, like some containers, they need fundamental different APIs. So for example, intrusive containers, right? We don't have anything in the standard. It feels like that creates problems, like having a common idiom, right, for everyone to follow. Does that problem also expand to other kinds of containers? So how do you feel like how complete the STL is in that regard?
Well, I would hope nobody would think that the STL is complete. That's what I said. You extend it, right? New containers, new everything. Boost has some intrusive containers because there are some trade-offs with intrusive containers. The beauty of the generic non-intrusive approach is you can put anything in a container, anything that's a regular type, and it doesn't need to be derived from some base class that says I'm a containable or a containee or something.
Sure, but my question is more about, like, for example, the intrusive containers, they require idiom, right? To, for example, how do you embed the node in? So every container, intrusive container out there is doing something different or a little bit different, and we don't have, the STL doesn't provide an idiom there. It feels like, how can we say the intrusive list is an STL container if it like fundamentally requires, a way to go about it, an API that's way outside of what the STL talks about, right?
I think it's possible to extend the conventions themselves. Again, the beauty of this set of conventions is that they're not constraining. You can make them work in interesting ways, and if you have a container that doesn't quite fit, like Vector itself doesn't support push front, well, just don't do it, and it'll work with the parts of the it'll work with the parts of the STL that it will work with, and if it doesn't, you'll get a compiler. Right? Okay, well, that looks like that's the questions, and I really want to thank you all for being here and putting up with my coffee. Thanks a lot.